Tesla has begun large-scale operations at Giga, Texas,
We start to large-scale.
with the completion of the installation of all equipment for the 55,000-ton Giga press.
Installation of all the equipment in Giga, Texas with.
This machine is not incremental. It redefines what's possible in casting precision, structural integrity, and production speed, immediately shocking the entire industry. This is the future of car manufacturing, slamming into the present with the force of a freight train. So what makes this machine different from the previous generation? And why can it shatter all other automakers? This video will separate these two questions one by one and give a full insight into the transformative effects of this press. Stick around for a full technical analysis that will change how you see car manufacturing. Make sure to hit subscribe and turn on notifications, because when this channel hits 20,001 subscribers, that's when things start getting really interesting. This video pulls together everything we've covered about Tesla's new Giga press and the Model 2 production line. Some details may sound familiar, but there are fresh breakthroughs, new leaks, and critical context you won't find anywhere else. Sit back. This is where all technologies finally collide into one explosive story. 1. How does the 55,000-ton Giga press redefine casting precision over past models? Step into Giga, Texas. Tesla's first Giga press in 2020 was a 6,000-ton workhorse. This is impressive, absolutely. But it's like comparing a pickup truck to a semi-hauler. Fast forward to 2025, and the 55,000-ton Titan isn't just bigger. It's a precision siege engine, clamping with 9 times the force of those early models. So what hidden engineering leaps turn this press into a calculated scientific breakthrough? Let's start with the raw physics. At 55,000 tons, that's 110 million pounds of clamping force. This press injects molten aluminum at 1,300 degrees Fahrenheit, under pressures hitting 15,000 pounds per square inch. In comparison with the prior generation, which is 6,000 to 9,000 tons. This 55,000-ton press is topping out at 10,000 pounds per square inch. Take a clearer view. Early Model Y rear sections used 6,000-ton presses to consolidate 70 parts into one, weighing 187 pounds total. This new beast handles over 300-pound single underbodies with 0 weld seams and an estimated 25% less material waste. The previous 9,000-ton Giga press handled rear underbodies up to 236 inches long. This 55,000-ton version extends to 300 inches, molding entire front-to-rear frames in one shot. Its hydraulic rams now run dual 10,000-pound per square inch circuits, distributing force evenly across a 1,000-square-foot mold. This reduces stress points by 40% compared to the segmented casts of 2020 models, where welds failed at 25% higher rates under crash tests. Material flow has been revolutionized entirely. Integrated vacuum-assisted die venting. Older presses vented gases at 80% efficiency, risking microbubbles that weaken casts by 15% in crash tests. The 55,000-ton upgrades to dual-zone vacuums pulling 28 inches of mercury, driving voids down to under 0.5%, based on Tesla's internal Fremont logs leaked in Q3 2025. That means underbodies resisting heat warping up to 1,800 degrees Fahrenheit, not the 1,200-degree limit of stamped steel. The press's vacuum-assisted injection pulls air bubbles to under 0.01% void ratio versus 0.5% in 2017 prototypes that led to 15% scrap rates. At 55,000 tons, this achieves 25% faster solidification, locking in high-strength 6061 T6 aluminum with 45,000 pounds per square inch yield strength, up from 35,000 pounds per square inch in multi-part welds. Thinner, but stronger structural elements. Reduced weight, enhanced crash resilience. Each frame is uniform at a molecular level, preventing micro cracks and long-term fatigue that traditional welds develop over years of stress cycles. Previous generations clocked 120 to 150 seconds per cast. idling 20% on cooldown. This one's adaptive servo hydraulics, borrowed straight from aerospace tech, shave it to 75 to 90 seconds, boosting output from 100,000 units per year to 450,000. At Giga Texas's 20-hour shifts, that's 1.2 million underbodies annually, enough for 600,000 Model 2s. And this marks a strategic leap for Tesla, while legacy lines like GM are still chugging at 200 seconds per part. Then there's the sleeper upgrade. Specifically, modular die inserts with 3D printed cooling channels. Old dies lasted 50,000 cycles before cracking under thermal stress. These hit 150,000 with embedded channels reducing hot spots by 40 degrees Fahrenheit. Tooling cost drops from $1.5 million per set to $900,000, contributing to the affordable pricing of rumored next-gen EVs like the Model 2. In practical terms, fewer factory defects mean your EV's frame holds up to 10,000-pound impacts without buckling. No other automaker has attempted a press this large, which is the engineering challenge alone that took over 3 years of development and tens of millions of dollars in R&D. It's frustrating to watch a vehicle weaken year by year, and for retirees, those repair bills really add up. Tesla's 55,000-ton Giga press changes that entirely. Your vehicle stays solid through coastal humidity, sudden storms, and decades of driving. Picture your grandkids climbing in years from now, and that car still feels sturdy, safe, and dependable. And if you could eliminate just one weakness from your current vehicle, including rust, weld failure, or frame fatigue, which would matter most to you? Let's drop 55,000 ton in the comments if this level of structural integrity is what you've been waiting for. The ripple effects don't stop at Tesla's factory floor. Let's explore how the 55,000-ton Giga press will reshape traditional auto manufacturing in ways legacy lines can't touch in the second section today. Because once you understand the production economics this machine unlocks, the competitive landscape starts looking very different. 2. How will the 55,000-ton Giga press disrupt traditional auto manufacturing? This isn't just a bigger machine, it's a cost revolution. Traditional stamping lines for underbodies carry tooling costs of $2.50 per pound, employing 200,000 workers across Michigan alone. The 55,000-ton Giga press slashes that to 75 cents per pound, reshaping supply chains and forcing the industry to rethink every assumption about EV production. The bigger question is clear. How can one machine force legacy giants to rethink $100 billion in annual tooling when their weld-heavy processes lag 50% behind in throughput? In comparison, traditional welding methods require 70 parts per chassis, with tooling costs ranging from $2.3 million to $3.4 million for 100,000 units, plus an additional 40 hours of labor per chassis. In contrast, the Giga press is a $6 million machine that amortizes to just $1.2 million in tooling costs, requiring only 10 hours total. That's a 40% savings, confirmed in Tesla's Model Y data. By 2026, this process could drive $800 per car reductions across the industry. Hyundai is already testing this on its 2027 Ioniq, anticipating annual savings of $500 million. Supply chain sterilization. Older methods require 1.2 tons of steel per chassis, sourced from up to 50 suppliers, creating logistical nightmares, especially in high-traffic ports like New York. The Giga press uses just 0.8 tons of aluminum from 5 suppliers, with materials localized at Tesla's Gigafactories. Tesla's 2025 Q3 report shows a 25% reduction in freight costs, saving $450 million. For Florida-based shippers, fewer delays mean EVs reach dealerships 15% faster, especially useful when avoiding seasonal disruption from hurricane shortages. Repair paradigms flip entirely. Underbody repairs for welded frames average $1,800 after a 30 miles per hour crash. For vehicles built with the Giga press, modular swaps replace the old repair process, bringing the cost down to $600 with 50% less downtime. Legacy car manufacturers like Toyota are now investing in 30,000-ton presses for their 2026 EV lines, but are 18 months behind, as reported by Nikkei. Fatigue life also leaps. Stamped parts begin cracking after 150,000 miles under 5G loads. Giga press castings endure 250,000 miles at 7G, verified through finite element analysis by IDRA's 2025 upgrades. For drivers in Texas, this translates to 20% fewer breakdowns on I-10 highway trips. Tesla's fleet telemetry data backs this, which is 98.7% uptime compared to just 92% for competing EVs. The impact on the EV market is undeniable. General Motors' Ultium platform, which was once the leader in the EV market, is now seeing a 15% market share loss due to widespread adoption of Giga casting. The speed difference is brutal. Tesla's Model Y can be fully assembled in just 10 hours, while competitors are still taking 30 hours. Analysts estimate any competitor trying to replicate Tesla would need $200 million to $300 million investment and 3 to 5 years, giving Tesla a multi-year monopoly on this manufacturing advantage. This is the EV industry reducing costs in ways that could directly translate to a more affordable, reliable EV. Tesla isn't just faster, they're smarter, and competitors are years behind trying to catch up. So, which manufacturing advantage matters most to you as a buyer? Let's type 1 in the comment for lower repair costs, type 2 for longer vehicle lifespan, or type 3 for faster production, bringing prices down. Which is your choice? Let us know below. Your answer tells us what analysis to prioritize next. The assembly lines are already moving. Giga Texas isn't waiting for competitors to figure this out. Mass production for 2026 is locked in, and the first castings are already being tested under loads that would buckle traditional frames. While legacy automakers scramble to retrofit decades-old factories, Tesla's 55,000-ton Giga press is churning out underbodies at a pace the industry hasn't seen before. For us, cheaper EVs, stronger frames, and a manufacturing gap so wide that our next vehicle purchase might come down to who mastered this technology first. The $800 per car savings, the 250,000-mile durability, and the 98.7% uptime aren't projections anymore. Their production realities are reshaping what we'll be driving in 2 years. If this breakdown gave you clarity on where the EV market is actually heading, hit that like button. Tesla has repeatedly said that.
We can make lower-cost products that are still efficient and compelling, and we can make them at scale.
The Tesla Model 2 is the clearest example of that promise. With a projected price far below current Tesla models, it is becoming the most anticipated car in the lineup because it promises a durable electric vehicle that needs very little maintenance, reduces long-term costs, and stays modern for many years without feeling outdated. However, what truly sets it apart happens inside the factory, where Tesla has activated a new generation of manufacturing that experts describe as an industrial miracle. The next generation, 50,000-ton Giga press. This massive machine reshapes how Tesla builds the vehicle frame, allows production speeds never seen before, and enables the possibility of creating multiple EVs in a single cast. Something Elon Musk himself hinted at, and the industry immediately noticed. What exactly is the 50,000-ton Giga press? The Giga press is a gigantic high-pressure aluminum die casting machine produced by IDRA Group in Italy, used by Tesla to create large monolithic vehicle structures. The machine has a clamping force of about 55,000 to 61,000 kilonewtons, equivalent to roughly 5,600 to 6,200 tons of force, strong enough to keep the mold sealed while molten aluminum is injected under extreme pressure. The Giga press is extremely large and heavy. Each unit weighs around 410 to 430 tons. Its enormous dimensions make it look like a small building inside the factory, something many people thought belonged in a science fiction film. Instead of building the vehicle frame by welding dozens or hundreds of metal pieces as the automotive industry traditionally does, Tesla uses the Giga press to cast large sections such as the underbody, floor, or lower chassis in one single casting. With this method, the frame is created as a solid, unified piece. Small parts, many welds, and complex multi-step assembly stages are eliminated. Each casting cycle, if operating at about 80 to 90 seconds, can create around 40 to 45 parts per hour, which equals roughly 1,000 parts per day when running continuously. With such high output capability, the GigaPress enables scalability, helping Tesla reduce cost, increase production, and deliver vehicles like the Model 2 at a more accessible price while maintaining quality. Thanks to characteristics such as massive pressure, enormous size, the ability to cast large monolithic structures, and high throughput, the GigaPress is not just a die-casting machine. It transforms how people think about car manufacturing, shifting from assembling many small welded parts to single-piece castings that are stronger, simpler, and faster. For the Tesla Model 2, this means a vehicle built with a unified frame, fewer separate components, and therefore a lower cost while preserving durability, a clear benefit for users. Do you think the Tesla Model 2's monolithic frame cast is stronger than traditional multi-piece assembly? Comment GigaPress if you agree. What makes the 50,000-ton GigaPress strong enough to shape an entire car frame? The 50,000-ton GigaPress used for the Tesla Model 2 is a gigantic die-casting machine designed to create monolithic vehicle frames with maximum precision and durability. The entire machine is wrapped inside a massive steel structure about 20 meters long, 6 meters wide, 6 meters tall, and weighing nearly 420 tons. It is strong enough to withstand up to 61,000 kilonewtons of force, equivalent to about 6,200 tons. This steel frame holds the internal systems from the melting chamber and holding furnace to the mold assemblies. Inside the machine, the melting chamber contains aluminum and a special alloy developed with support from SpaceX. It can withstand temperatures up to 850 degrees Celsius and holds about 500 kilograms of molten aluminum, ready for casting. Next to the melting chamber is the holding furnace with nearly 600 liters of capacity, keeping the aluminum stable at 750 to 850 degrees Celsius. It is covered with a nitrogen blanket to prevent oxidation and uses argon and silicon carbide filtration to ensure the metal remains clean and homogeneous before entering the mold. The mold system is the most important component. The machine is equipped with 7 molds operating simultaneously. Each mold is 3.5 meters wide, 4 meters long, and 1.2 meters deep, and can withstand the strong pressure of high-speed pistons. The pistons can inject aluminum at speeds up to 10 meters per second, balanced precisely so the aluminum fills the mold completely without air bubbles or premature cooling. The integrated vacuum system removes air inside the mold, reduces porosity, and increases structural strength. The Giga press also includes an ultra-fast cooling system that reduces the frame temperature from about 400 degrees Celsius down to 50 degrees Celsius in only a few seconds. AI-powered sensors including X-ray, thermal, and pressure sensors continuously monitor the casting quality inside the mold. With such scale and engineering, the Giga press is capable of casting multiple frames simultaneously, creating a fast, efficient, and high-quality production foundation for the Tesla Model 2. How does the 50,000-ton Giga press turn molten aluminum into a complete car frame in just a few seconds? The 50,000-ton Giga press process begins with preparing purified molten aluminum. Each mold requires about 80 kilograms of metal. The aluminum is placed inside the 600-liter holding furnace, where it maintains the correct temperature and viscosity before entering the mold. Keeping the aluminum within a stable temperature range is critical, because if it is too hot, it creates air bubbles, and if too cold, it solidifies before filling the mold, causing structural defects. When the material is ready, the surface of the mold is coated with a thin layer of release oil, that helps the molten metal fill complex shapes without sticking. The vacuum system activates and removes all air inside the mold, minimizing porosity and improving uniformity. This is essential because Tesla Model 2 monolithic frames have complex shapes with channels, pockets, and load-bearing geometry that require flawless metal flow. The molten aluminum is then injected into the mold at about 10 meters per second by the high-speed piston, generating up to 61,000 kilonewtons of pressure. The force and speed must be precisely controlled to fill every detail without defects while maintaining monolithic structure. Technical analysis shows that with the piston speed, vacuum system, and special release coating, dimensional error can be kept below 0.1 millimeter, ensuring the Model 2 frames remain consistent and meet strict engineering standards. After the aluminum solidifies, the mold is cooled quickly, reducing the frame temperature from about 400 degrees Celsius to near 50 degrees Celsius. The frame is removed by robots and transferred to the next stages. Throughout the process, AI sensors monitor temperature, pressure, and X-ray patterns in real time. This ensures quality while reducing post-inspection time, allowing each casting cycle to complete in only a few seconds. With this system, the Tesla Model 2 is built with a unified structure that minimizes joints and mechanical weak points. Technical analysis shows that compared to traditional manufacturing, using vacuum systems, high-speed pistons, and AI inspection reduces the risk of porosity to below 0.5%, while increasing stiffness and load-bearing capability. The entire closed loop from molten aluminum to the finished frame takes only a few seconds per shot, explaining why Tesla can claim that a Model 2 frame can be completed in an extremely short time. Is it true that the 50,000-ton Giga press can produce 7 EV frames in a single shot? The 50,000-ton Giga press can cast 7 EV frames at the same time, which is a major breakthrough for the Tesla Model 2. Thanks to its massive structure and extreme strength, it can hold 7 molds simultaneously, while molten aluminum is injected into all of them in one single casting. This means one machine cycle does not produce only one part, but 7 monolithic frames, reducing time and effort compared to the traditional multi-piece method. More surprisingly, the Giga press can operate in multi-model mode, rather than producing only a single mold design. This capability becomes even more efficient because the Model 2 and Cybercab share 70% of their design. This allows the Giga press to switch between models easily, optimizing productivity without interrupting the casting process. When the machine runs continuously, each hour it can produce 35 frames across 7 vehicles, or about 280 frames per day, delivering extremely high throughput with stable quality. This achievement is not only about speed, but also scale. Producing 7 frames at once enables rapid expansion, allowing Tesla to bring the Model 2 to an affordable price while maintaining high durability and quality. The concept of 7 EVs at once is therefore not just a number, but proof of how Tesla uses advanced technology to transform the automotive manufacturing process from assembling many joined pieces into creating unified frames that are stronger, simpler, and faster. This directly benefits Tesla Model 2 users with a more durable, consistent, and affordable vehicle.
And one of the things we've done is create the largest castings that have ever been done. And they're very complex castings.
If you've ever stood in a cold parking lot struggling to open a heavy door, wondered why small cars today still feel cramped, or questioned why modern vehicles keep getting more complicated instead of more intuitive, Tesla now claims it can solve those problems by building a car every 7 seconds from a single reinforced casting. How can a 55,000-ton press shrink production time to 7 seconds without compromising strength? The core promise of the new 55,000-ton Giga press isn't just raw force. It's the ability to collapse what used to be a 120-step assembly process into a single automated sequence that finishes in roughly 7.2 seconds per casting. For comparison, today's largest widely used automotive presses from competitors like Idra or Buehler operate in the 9,000 to 12,000 ton range, producing medium-sized castings that still require welding, bolting, and subframe alignment. Those machines need anywhere from 38 to 52 seconds per cycle, depending on part complexity. Tesla's new unit is nearly 5 times larger in clamp force and cuts cycle time by an order of magnitude, something the rest of the industry hasn't even begun testing at scale. The way Tesla does this is by pushing metallurgical limits in a direction almost no automaker is prepared for. Instead of relying on standard high-pressure die-casting aluminum mixes, the 55,000-ton press uses a modified alloy with faster flow rates and higher thermal tolerance. That lets the molten metal fill a chassis mold more than 4 meters long without microfractures or cold joints, even when injected at extreme velocities. A casting that size usually warps during cooling, but Tesla's new parallel quench channels keep dimensional variance below 0.8 millimeters, tight enough for senior drivers to benefit from smoother door alignment, quieter cabin seals, and more precise mobility assistance systems. Another breakthrough is the press's dual shot system. Traditional Giga casting relies on a single injection, but Tesla's prototype adds a secondary micro-infusion step that strengthens stress zones near the hinge pillars and sill plates, areas that take load when a driver leans on the door for support. For seniors who routinely bear weight on the door frame when entering or exiting the car, this reinforcement directly translates to long-term structural stability rather than gradual flex or sag over time. And then there's energy efficiency. A press this large should realistically draw upwards of 20 to 24 megawatts per cycle, but Tesla's regenerative hydraulic system recaptures kinetic energy to bring net consumption down to around 11 megawatts. That reduction is what allows a 7-second takt time without overheating or deforming the mold. If the system ran at full brute force, production would bottleneck in minutes from thermal stress. With Tesla's closed-loop cooling, it can theoretically sustain over 10,000 cycles per day, enough to produce the full Model 2 daily output from a single line. When you combine all of that with Tesla's vertical integration, from alloy mixing to mold machining, the cost per body target falls close to $198 per cast, which is dramatically lower than the $780 to $1,050 cost range for multi-part steel assemblies among mainstream automakers. Why is Tesla targeting seniors, first with a machine? This powerful. Over the last 2 years, accident statistics from multiple transportation agencies have highlighted the same pattern. Seniors are involved in fewer high-speed collisions, but they experience a dramatically higher rate of parking lot impacts, low-speed side scrapes, mobility-related entry-exit injuries, and door angle accidents. To address this, Tesla wants the Model 2 for seniors to start life with a body that is fundamentally more rigid, lighter, and more consistent than a traditional steel frame compact. A single-piece casting made in 7 seconds gives engineers a predictable structural foundation, something that matters enormously when designing the car's senior-first ergonomics. When you know every body shell is within the same tight structural tolerance, you can tune things like door counterweighting, hinge torque, grab handle positioning, and step-in height with confidence that the geometry won't shift across production batches. By producing a larger integrated lower body casting with reinforced sill plates and hinge posts, Tesla can install extra-wide doors without sacrificing rigidity. That directly helps older drivers who need more space to swing their legs in or who rely on the door frame for stability. It also reduces the lateral torsion that happens when someone leans heavily on the door, which is a common cause of door sag in older vehicles. With the new Giga structure, Tesla expects long-term hinge drift to be so minimal that even after 150,000 miles, the door should still close with the same alignment and force as day one. Then there's safety. A unified casting provides more predictable crumple behavior during low-speed impacts. Parking lot collisions, like getting clipped when opening the door or being sideswiped while backing out, are exactly the scenarios where seniors have reported anxiety, because they can be difficult to judge spatially. Tesla's engineers have used the massive stiffness of the 55,000 T body to carve out localized deform zones around the wheel arches and door edges. The casting compresses precisely where it should, preventing force from transferring into the cabin. Smaller, inconsistent multi-piece frames simply cannot guarantee that kind of repeatability across millions of vehicles. The timing also matters. Over the past year, the EV market has stalled for younger buyers, but surged among older ones. Seniors value reliability, low maintenance, and predictable costs, not 0 to 60 bragging rights. With a single-piece casting, Tesla reduces long-term maintenance dramatically. No rust-prone weld points, no alignment drift, fewer squeaks, fewer rattles, fewer mechanical points of failure. And while Tesla isn't publicly saying it, suppliers close to the project have hinted that the Senior Edition's platform will be designed to accommodate future assisted mobility add-ons, like powered door actuators calibrated for gentle opening, or grab rail accessories that lock directly into the casting's reinforced zones. You can't offer features like that without an ultra-consistent body structure, and that consistency only comes from a press that can repeat the same shape every 7 seconds with near-zero variance. How does a 55,000 T GigaCast platform reduce costs? Enough to make the Senior Edition truly affordable? A traditional compact car requires over 400 stamped panels, welded into subframes, sealed, coated, and then bolted into a final body structure. Every step adds labor hours, energy costs, and tolerance drift. Even efficient Japanese and Korean platforms still average 18 to 22 labor hours per body in white, largely because human operators and robotic welders must alternate in tight cycles to avoid overheating and misalignment. The new Giga press reduces that entire chain to a single casting plus 2 reinforcement inserts, bringing the body in white labor time down to roughly 3.5 hours. That alone cuts several $100s off the manufacturing cost. But the real savings come from removing dependencies. No weld lines to maintain, no alignment jigs to recalibrate every shift, no rework stations pulling bodies off the line due to tolerance errors. On a high-volume platform like the Model 2 Senior Edition, this streamlined workflow drives projected body-in-white costs to well under $300 per unit, a number previously reachable only with decades-old steel unibodies. Energy costs drop too. Because the press operates on Tesla's regenerative hydraulic loop, it consumes up to 40% less net electricity per cycle than a conventional large casting machine. Over a year of continuous operation, that difference can shave millions off plant-level operating expenses, money Tesla can redirect toward adding mobility features like powered doors, anti-pinch sensors, or structural padding at entry points, features that older drivers directly benefit from. Even shipping and logistics are cheaper. A one-piece cast body eliminates dozens of supplier shipments, reducing freight requirements by an estimated 290 kilograms of transported material per vehicle. Components that once took weeks to arrive can now be produced on-site in a just-in-time rhythm. Faster logistics means Tesla can scale production rapidly the moment demand spikes, something especially important for the Senior Edition, which analysts expect to surge quickly once word spreads that it's easier to enter, exit, and operate than most gasoline compacts. And then there's the part most automakers overlook: service economics. Seniors tend to keep cars longer and drive fewer miles each year, which shifts total cost of ownership toward maintenance rather than depreciation. A GigaCast car has fewer parts that can loosen, rust, or misalign. If a door closes straight for 15 years instead of 6, or if the body doesn't develop vibration points over time, that dramatically extends the vehicle's usable lifespan. Tesla's internal projections, at least from what is leaked, suggest that the Senior Edition could maintain structural integrity beyond 300,000 miles, allowing the company to extend warranty packages or bundle service support in ways legacy automakers simply cannot match at the same price. Now I want to hear from you. Would a simpler, sturdier EV make you more confident driving as you get older? Do you think other automakers will follow Tesla's lead and build senior-focused models? And what feature do you believe matters most? Easy entry, wide swing doors, or long-term reliability? If you're tired of shelling out for gas guzzlers and endless repair bills, Tesla's latest move is about to flip the script on car ownership.
I mean, Elon's just a visionary, somebody who continues to just push the boundaries, looking for a future that we really want to aspire to be in.
That's what Tesla's chief designer Franz von Holzhausen said. As we hit December 2025, Elon Musk's crew has finally cranked up the production line for the Model 2 at Giga, Texas, promising an EV that slashes costs so low it could make traditional car expenses a thing of the past. But how exactly did Tesla pull this off? How is the Tesla Model 2's $14,999 starting price set to crush rivals, like the $26,595 Chevy Bolt EUV? Tesla's Model 2 is hitting the scene as the ultimate budget EV, clocking in at a base price of just $14,999 before incentives, according to fresh leaks from Fremont factory insiders. That's not some pie-in-the-sky figure. Elon Musk confirmed during the Q4 2025 earnings call that this compact crossover undercuts the market by leveraging next-gen battery tech and streamlined design. Compare that to the Chevy Bolt EUV, which starts at $26,595 for its 2025 model year, and you're looking at an immediate $11,596 pocketed right off the lot. Or take the Nissan Leaf at $28,140. The Model 2 shaves off over $13,000 while packing similar urban utility. But the real kicker? Apply the federal $7,500 EV tax credit and effective cost drops to $7,499 for qualifying buyers, making it cheaper than many used gas cars on Craigslist. Tesla achieves this by ditching unnecessary frills. The Model 2 measures about 170 inches long, shorter than the Model 3's 184 inches, with a wheelbase of 110 inches for nimble city handling. It seats 5 comfortably, offers 20 cubic feet of cargo space behind the rear seats, expanding to 45 with them folded, and weighs in at around 3,200 pounds, lighter than the Bolt's 3,680 pounds, which boosts efficiency. Power comes from a single-motor rear-wheel drive setup, delivering 200 horsepower and 250 pound-feet of torque, sprinting 0 to 60 miles per hour in under 7 seconds. Dual-motor all-wheel drive variants bump that to 300 horsepower for $18,999, still undercutting the Bolt's single trim. Battery-wise, it's fitted with a 53 kilowatt-hour LFP pack from CATL, good for 250 miles of EPA range on the base model, 250 miles of EPA range on the base model, or up to 300 miles on higher trims, matching the Bolt's 259 miles, but with faster 150 kilowatt DC charging that hits 80% in 25 minutes versus the Bolt's 38 minutes. This pricing strategy isn't guesswork. Tesla's supplier bids last year targeted 10,000 weekly units, scaling to 520,000 annually by 2026. Against BYD's Seagull, priced at $9,700 in China but unavailable stateside, the Model 2 positions Tesla as the U.S. affordability king. Early testers report a minimalist interior with a 15-inch central touchscreen handling all controls, no physical stalks, and over-the-air updates that keep software fresh without dealer visits. For tech-savvy drivers, this means seamless integration with Tesla's app for remote preconditioning and navigation, features that add $2,000 plus as options on competitors like the Hyundai Kona Electric at $32,675. Shifting gears to the heart of this breakthrough, Tesla's production wizardry is what makes these numbers possible, turning assembly into a high-speed symphony that's light years ahead of old-school Detroit lines. How is Tesla's unboxed production line at Giga, Texas, slashing assembly time? Forget conveyor belts dragging cars through endless stations. Tesla's unboxed manufacturing process at Giga, Texas, is revolutionizing how EVs roll off the line, clocking in a Model 2 from start to finish in under 45 minutes. That's half the time of traditional methods, like Ford's F-150 line that takes 90 minutes per truck. The secret? Parallel subassemblies where front, rear, sides, and underbody are built simultaneously in dedicated zones, then snap together like Lego bricks in a final merge. Each station handles tasks in just 19 seconds, per Musk's declarations in recent factory tours, compared to the industry average of 60 to 90 seconds seen at GM's plants. This efficiency stems from robotic arms, over 1,000 per line, handling 95% of welding and painting, reducing human intervention to quality checks. Giga, Texas, spanning 10 million square feet, dedicates 2 million to Model 2 lines, with initial output at 200 vehicles per day ramping to 2,000 by mid-2026. Cost savings are massive. The unboxed method cuts floor space by 50%, needing only 1,000 square feet per vehicle versus 2,000 for linear lines, and trims labor costs by 40% through automation. Tesla's 4680 battery cells, produced on-site at 20 gigawatt-hours annual capacity, integrate directly into structural packs, eliminating 370 parts compared to the Model 3's setup. This drops battery costs to $50 per kilowatt-hour, half of 2020 levels, enabling that sub-$15,000 price. Toyota's lines average 50 vehicles per hour. Tesla aims for 100, potentially producing 500,000 Model 2s yearly by 2027, dwarfing Volkswagen's ID.2 projected 200,000 units at $27,000 each. How many tons of aluminum does one Giga press save Tesla on every single Model 2 body? While the unboxed process steals most headlines, the real unsung hero quietly crushing the competition is the latest generation 9,000-ton Giga press that Tesla just fired up on the Model 2 line at Giga, Texas. For reference, the original 6,000-ton presses used on the Model Y cast the rear underbody in one single piece. The new 9,000-ton monsters go bigger. They swallow 180 pounds of molten aluminum in one shot and spit out the entire rear floor plus side rails in a single 90-second cycle, replacing what used to be 72 separate stamped parts and 1,600 welds on a traditional compact car. That single casting weighs 138 pounds when it comes out, cuts 44 pounds of structural weight versus the old multi-piece design, and shaves roughly $18 off the per-vehicle cost in materials and labor alone. Do the math across a planned 520,000-unit annual run, and you're looking at Tesla saving north of $9 million a year, just on the rear casting, not counting the front casting that's now handled by a second 9,000-ton press doing another 60-plus parts in one hit. Cycle time is insane: 19 seconds to inject, 45 seconds to cool and extract. Then the die opens and the robot grabs the next red-hot piece. That's less than 2 minutes from liquid metal to finished structural component, compared to the 12 to 15 minutes it takes legacy automakers to stamp, weld, and rivet the equivalent assembly. Tesla runs 4 of these 9,000-ton beasts on the Model 2 line alone, 2 front, 2 rear, giving the factory a theoretical capacity of roughly 120 complete structural sets per hour before you even count the side and roof assemblies. The ripple effect is brutal for competitors. A comparable Honda Civic body in white uses over 400 separate pieces and 3,000 welds. The Model 2 does it with fewer than 30 major castings and under 400 welds total. That's why Tesla's structural rigidity numbers are coming in at 38,000 Newton meters per degree, better than a Porsche 911 GT3, while still dropping curb weight to that featherweight 3,200-pound target. How could owning a Tesla Model 2 with 300-mile range and zero gas needs save you? Imagine ditching $200 monthly gas bills forever. The Model 2's all-electric setup with home charging at 12 cents per kilowatt-hour costs just 40 cents per mile versus 15 cents for a gas car like the Honda Civic. over 12,000 annual miles, that's $480 in electricity against $1,800 in fuel, pocketing $1,320 straight away. Add low maintenance, no oil changes, fewer brake replacements thanks to regenerative braking, and Tesla estimates $3,000 saved over 5 years compared to the Civic's $4,500 upkeep. The 300-mile range on premium trims means fewer stops. Base models hit 250 miles, still beating the Civic's 400-mile tank, but without emissions or $50 fill-ups. Real-world tests show 4.5 miles per kilowatt-hour efficiency, so a full charge runs $6.36 at home rates, covering what a 30 miles per gallon Civic needs $45 in gas for. Factor in no transmission fluid or belts, and lifetime costs drop to 25 cents per mile, undercutting the industry's 60 cents average. Autonomy amps it up. Standard full self-driving hardware enables supervised autopilot, potentially reducing insurance by 20% or $300 yearly via Tesla's data-driven policies. Project 500,000 miles without major repairs, thanks to over-the-air fixes that resolved 80% of issues remotely in 2025 fleets. Against the Ford Mustang Mach-E at $42,995 with $0.06 per mile costs, Model 2 saves $720 annually on energy alone. So what do you guys think? Will the Model 2's range and autonomy convince you to switch from gas? How much would you save ditching fuel bills? Drop your thoughts in the comments below. If this breakdown fired you up, hit that like button, subscribe to autogearshift, and turn on notifications so you catch every update hot off the press. Every few years, the auto industry hits a turning point. And this week, Elon Musk did exactly that.
Elon Musk is unique, totally unique in that aspect.
For the first time, Tesla confirmed the deployment of a new 51,000-ton Giga press in Texas, a machine powerful enough to form the entire rear structure of the Tesla Model 2 in just 5 seconds.
There's nobody I've been bumped into that has his depth of knowledge.
How can a 51,000-ton press reshape the entire Model 2 production line in just 5 seconds? The scale of the new 51,000-ton Giga press becomes clear only when you compare it to today's largest die-casting machines. Until recently, the industry standard hovered around 13 million to 18 million pounds of clamping force, with only a handful of experimental systems pushing toward 25 million pounds. Even Tesla's own 9,000-ton press, used for the Model Y, was once considered a borderline engineering stunt. Now, Tesla is stepping into a completely different class of machinery, one delivering roughly 102 million pounds of clamping force, about 5 times stronger than anything a legacy automaker currently operates. At this size, the press is capable of injecting more than 440 pounds of molten alloy into a mold and locking it with enough force to form a single-piece rear underbody in 5 seconds, including fill, solidify, and eject. Speed alone isn't the story. This level of force allows Tesla to shrink a structural section that normally requires 120 to 160 welded components into one massive casting. That removes dozens of robots, hundreds of weld points, and several production stations. In an industry where every robot often costs tens of thousands of dollars per year in maintenance and calibration, eliminating entire blocks of the assembly line is what gives Tesla the economic room to target a sub-$25,000 Model 2. Analysts estimate that a single-piece casting could shave $1,000 to $1,800 off the production cost per vehicle, depending on metal yield and how many castings Tesla ultimately uses. But the real disruption is cycle time. Traditional stamping and welding lines can take 8 to 12 minutes to fabricate the same underbody structure, depending on the number of welded joints and material thickness. With a 5-second casting cycle, even factoring in mold cooldown, Tesla could realistically output more than 600 completed underbodies per hour from a single 51,000-ton machine. By comparison, Toyota's fastest consolidated stamping lines peak at around 45 bodies per hour, and Volkswagen's MEB line averages roughly 38 to 52 per hour at its US and European facilities. This is why Elon Musk calls the Giga press the first machine that builds the machine. Its throughput is so high that it forces the rest of the factory to accelerate, driving redesigns in conveyors, pack installation, material flow, and even building layout. At Giga, Texas, the new press is expected to anchor an optimized Model 2 line designed specifically around single-piece castings. That translates into shorter lines, fewer workers per vehicle, smoother automation, and more consistent quality. Because every casting comes out either perfect or gets immediately recycled. And that's the part older drivers tend to appreciate most. Fewer welded joints mean fewer long-term failure points. When castings replace dozens of individual stamped parts, parts that typically loosen, rattle, or corrode over time, you end up with a stiffer, quieter structure that stays solid even after 200,000 miles of real-world American driving. Why is Tesla using a new alloy formula, and what does it mean for Model 2 durability and safety? The jump to a 51,000-ton press isn't just about force. It demands an entirely new alloy engineered to survive extreme thermal and mechanical stress. Traditional automotive aluminum alloys struggle when injected under pressures exceeding 100 million pounds of clamp force, often cracking during rapid cooling or developing internal porosity that weakens long-term rigidity. Tesla's solution, according to engineers familiar with the Texas expansion, is a modified aluminum-magnesium blend, optimized for ultra-fast fill rates and high thermal stability, around 1,100 to 1,200 degrees Fahrenheit. What makes this alloy different is its ability to maintain structural integrity, even when shot into a mold in under a second. Instead of forming visible stress lines or weak spots, problems that historically forced automakers to weld multiple stamped panels, Tesla's formula creates a uniform grain structure strong enough to serve as a load-bearing single-piece frame. Early estimates suggest the new alloy can deliver 20 to 25% higher tensile strength compared to the mix used in the 9,000-ton Model Y castings, bringing it closer to the performance of certain aerospace-grade aluminum parts, but at automotive production volumes. This matters because a Model 2 body made from fewer but stronger pieces behaves very differently in real-world impacts. Instead of welds acting as failure points, the casting distributes crash forces across a continuous surface, improving energy absorption. Engineers project that even with a smaller and lighter body, the Model 2 could meet or exceed the 5-star IIHS and NHTSA crash standards that heavier vehicles often rely on sheer mass to achieve. And that's critical for older drivers, especially those looking for a compact EV without compromising on safety during highway travel at 70 to 80 miles per hour. At the same time, the alloy's heat tolerance allows Tesla to integrate more thermal pathways directly into the casting. This opens the door for future battery platforms that use the underbody as part of the cooling structure, similar to the approach used in Tesla's structural battery packs today. For the Model 2, engineers expect a battery footprint around 37 to 42 kilowatt-hours, with thermal loads potentially reaching 110 degrees Fahrenheit to 140 degrees Fahrenheit during fast charging. Integrating cooling channels into the casting could help stabilize temperatures faster, reducing long-term battery degradation and allowing more frequent high-power charging cycles for owners who rely on road trips or long daily commutes. Another advantage comes from weight savings. By eliminating dozens of steel brackets, reinforcements, and weld plates, Tesla is expected to remove 120 to 180 pounds from the rear structure alone. In a compact EV where efficiency is everything, that could translate to an additional 12 to 20 miles of range, or allow Tesla to shrink the battery pack while maintaining the same 240 to 270 mile target range. Either outcome drastically reduces cost. When battery cells account for roughly $60 to $80 per kilowatt-hour, a lighter pack could save Tesla several $100s per vehicle before the first Model 2 even rolls off the Texas line. What does a 51,000-ton press actually mean for you as a future Model 2 owner? For most people, giant casting machines and factory layouts sound like something only engineers care about. But with the 51,000-ton Giga press, the real impact isn't in the machinery. It's in what you get when you eventually sit behind the wheel. Because when a vehicle is built in 5 seconds instead of 10 minutes, and when 3,000 welds shrink to one solid casting, the long-term effects show up directly in your ownership experience. Fewer repairs, fewer rattles, fewer service visits, and a car that stays tight and quiet even after 100,000 to 200,000 miles. Let's start with reliability. Every welded joint is a potential future problem. Over time, welds loosen, corrode, or introduce small vibrations, especially for older drivers who value a stable, quiet cabin on long highway drives. By replacing 120 to 160 welded components with a single structural casting, Tesla dramatically reduces those future failure points. You're not just buying a cheaper car, you're buying one with fewer parts that can ever break. Think of it as the difference between a watch with 500 little screws and a watch milled out of a single block of metal. One needs maintenance, the other simply lasts. Then there's the cost over the life of the vehicle. A traditional automaker needs hundreds of robots and thousands of welds to produce a compact car. That overhead, labor, energy, calibration gets baked into the price you pay. It's one reason many affordable EVs still end up costing over $30,000 out the door. Tesla's 5-second casting cycle replaces entire welding halls, cutting what analysts estimate could be 30 to 40 hours of production labor per vehicle. When you eliminate those hours, you eliminate a big chunk of markup. That's how Tesla plans to keep the Model 2 under $25,000 without forcing buyers to accept cheap interiors or low-range batteries. Even maintenance becomes simpler. A one-piece rear underbody means fewer bolts to tighten, fewer seams to inspect, and far fewer components that can wear unevenly. For older drivers who don't want to spend Saturday mornings at a service center, this matters. A simpler structure also means fewer alignment issues after hitting potholes, something every American driver deals with, especially in northern states where winter roads destroy suspension components. And let's talk safety. A single casting distributes crash forces more evenly than dozens of smaller panels, which means the Model 2 could meet 5-star standards without relying on heavy steel reinforcements. If you're someone who spends real time on highways, 70 to 80 miles per hour driving, the confidence that a compact EV can protect you as well as a larger SUV is a huge deal. So would you trust a compact EV built from a single massive casting over a traditional welded design? Share your thoughts below. Your experience and perspective genuinely shape the conversations we build on this channel. If you enjoyed this breakdown, give the video a like, hit subscribe, and turn on notifications so you don't miss the next deep dive from AutoGearshift.